Power and Light in Atlanta, and he will speak about generalizing statistical mechanics. If you're okay, Carl, that we maybe do 18-minute talk and then maybe 2 minutes for questions. Is that okay?
Absolutely. I think I'm going to be under 15 on my talk.
All yours.
All right. Well, thank you so much. I want to talk more today about a problem that I came across when I was in graduate school. I took a microeconomics course, and my professor said, microeconomics cannot be aggregated into macroeconomics. And I thought to myself, as a nuclear engineer and as an engineer or practitioner of science, that, this just doesn't make sense. In nuclear physics, we deal extensively with the Stefan-Boltzmann transport equation and all the different methods of solving it, different time domains and all sorts of fun stuff. So we aggregate from the micro to the macro in physics all the time. And when I went and looked more at economics, everything was focused predominantly on the individual, at least in the formal sense in microeconomics. And this theory of game theory was generalized in 1968 into a subjective probability theory. And this generalization of subjective probability theory is going to be significant for what I'm going to do with it later. But to say that utility in a purely economic sense can be expressed as our knowledge of a state, or our knowledge of our observations of a society is all that we're saying here. Is a very weak statement. And it's really great in providing insights into the individual, but it still doesn't do very much to help with going from that to the group. So I turn to really probably one of the most clear foundations of statistical mechanics, and that was with Gibbs. And what Gibbs did was he started with the Hamiltonian for each particle, and he used that to express the knowledge of the state of the system in terms of probability, with its ability to be able to occupy phase space. And then he did something very interesting very early in the book, which was he took the logarithm of that coefficient of probability and he called it the index of probability. Well, the thing with that index of probability is that that's Shannon's uncertainty. And then he goes from showing from that uncertainty, and from that uncertainty derives the fundamental equation of thermodynamics, but where the entropy is not Boltzmann's S, it's Shannon's H. And this is a full 50 years before the development of information theory. So what Gibbs did was he aggregated the laws that we use in physics to describe the microstate into the macrostate in terms of information theory, not in terms of mechanics, but in terms of information theory. And this is a very important distinction because shortly after information theory came out, Edwin Jaynes took Gibbs and generalized it in his Information Theory and Statistical Mechanics paper in 1957. And what he did was he removed Gibbs' dependence on the Newtonian and quantum Hamiltonian, depending on which type of system you're talking about. And his generalization is very straightforward. It was basically a maximum entropy argument for this based on in terms of subjective probability. And there has been a significant amount of critique of Jaynes' work, but in those critiques, I haven't found anything that disproves it on the terms that it exists and what it claims to claim. So in order to talk about the difference between subjective and objective probability, we need to take a bit of an epistemological break. So there are two fundamental modes of reasoning that Jaynes identified. They've been identified elsewhere as well, and that is of the subjective and of the objective. And these two concepts are two very different modes of reasoning, but they always end up with the same results. And in order for us to be able to gain new insight into things, we really have to use both of them. I read a book recently that goes into this, is showing that the right brain is is specialized into subjective reasoning and that the left brain is specialized into objective reasoning. And the author talks about how both modes are needed for survival, and both modes are valid within their domains. And looking at it from a more mathematical standpoint, the subjective is propositionally weaker and more general as a result of being weaker, and the objective is propositionally stronger and therefore much more limited. So if we look at the sum total of what we experience as an individual, we can describe much of that with our subjective reasoning, and then a limited set of the subjective reasoning can then be described as objective. So the progression of our knowledge goes from experience to subjective understanding and then into objective understanding. So I think of objective as a very useful subset of subjective thinking. So I think Jaynes' observation on the use of subjective and objective probability is much more fundamental and is actually tied to the physical structure of our brains, which emerged out of evolution and is common in all complex organisms. So the bicameral brain is almost ubiquitous in intelligent life. So that evolution emerged out of evolutionary pressures in response to the physical reality around us over the last billion years or so. So my question is, which is more real and which is more correct? And to answer that, I would say neither and both at the same time, because it depends on what we can control, order, and what we can observe, chaos. So the subjective mind is more focused on what we can observe, and the objective mind is more focused on what we can control. And we need both. So one of my favorite quotes from Campbell is about taking the hero's journey. And so where I began in all this was where I probably least understood things. So for the derivation that I'm going to go through, it's going to be divided into three main parts, and it's pretty short. So we're going to start with Pfanzagl's definition of the measure space and use the utility that the utility is represented in that space. We can express our knowledge of that utility in terms of a probability density function. And then we're going to use Jaynes' generalization of Gibbs to determine the individual's utility function. And then from that, we're going to aggregate the individual into the group using the properties of Shannon's entropy. Now, there's going to be some serious limitations associated with it. So I'm not trying to make predictions here. I'm not trying to control things. I'm just trying to describe what we can see and what we can measure and what our experience is. So this is purely from a subjective basis. So begin. So we're going to assume we can express our knowledge of the utility of the individual's utility function in a specific format where the ph's are the moments of the probability density function, and that they are constrained by the expectations that are given there. If we define the 0th moment as phi 0 as being 1, then its constraint is also going to be 1. And this is the same thing as Gibbs' conservation of the extension in phase. And from this, what falls out is the partition function. So taking Jaynes' maximum entropy approach, we can then take the partition function that we have, we can differentiate it in terms to each of its parameters that are then subsequently constrained, and there's our maximum entropy probability distribution. And so what comes out of that is we end up with the fundamental equation of thermodynamics, not as a consequence of mechanics, but as a consequence of information theory, which is the same result that we found in Gibbs. So shifting over to Shannon, since entropy is additive, if we look at the probability for each individual, or the utility function for each individual, then as a group, all we have to do is just add all those individuals together. To make a philosophical break to simplify the math, we assume Rawls' veil of ignorance, so that we can't know. It's as if we don't know. If you had to pick who you were going to be in the society, you would have to do so from a veil of ignorance, is what is in his book. And so that means that each individual within that group are indistinguishable from each other. And that's how we aggregate from the micro into the macro in a formal sense. And so from this standpoint, we can think of statistical mechanics and the laws of thermodynamics are not consequences of the natural world. They are derived properties of the statistics we use to describe what we see and what we experience. And under a lot of work, we can be able to make some more accurate predictions associated with that. What's funny is that the path for thermodynamics actually, I think, came more from the objective and into the subjective with Boltzmann, and then Gibbs started from the subjective and moved into the objective, which I think is more natural. So continuing with economics, I want to look at the income distribution in terms of the measure of relative economic value of the contribution of each person to the society as judged by all the other individuals of the society. So this can be on the world, this can be on a country level. The income distribution is how we judge each other, I guess would be a way of saying it, and judging what our value is of it. That might seem harsh in today's world, but I think that is a fundamental truth. And that utility corresponds with each individual's ability to interact with the world around them. And as you can see by the graphs that we have here and in the data, that the income distribution, for the most part, is lognormal. That is at the more thermalized ends of it, I guess would be a way of describing it. At the upper ends, it follows a Pareto distribution, not a lognormal distribution. Both are related to each other. From our approach, if we select the set of fees, and that will result in the partition function that we have there, and then we will apply the following moment constraints, and that will result in that set of equations, and solving for that, our partition function is solely a function of the shape parameter for the distribution, and then our other two parameters fall out there. If we recall from doing a little bit of math, we can describe the expectation of the distribution. This is the arithmetic expectation of the distribution. The entropy falls into this form here, which should start to look a little familiar with what we've seen in physics and also in economics for that matter. And we determine the coefficient alpha based off of the relationship below. In practice, alpha is determined through the process of regression. If we take a look at that function in terms of extrema, what we find is that entropy is maximized for the shape parameter when sigma is equal to 1. And that has some pretty significant implications. So the entropy of the income distribution is maximized that when it's 1, and when it's flat, when Gini is 0, which is the target of what redistributive policies is, the entropy is negative infinity. So, well, what's entropy? And then if entropy always increases globally, what's its nature? Is it good? Is it bad? And there's been a lot of different words in order to describe what entropy is. Disorder, missing information. In my read of Adam Smith, I see his invisible hand as him trying to describe entropy. Or is it complexity, is what's been talked about here earlier in this the meeting. And I think when we think about it in terms of economics, that complexity is probably the best way of describing it. And I think Adam Smith saw it that way too. So we need to answer a question about how we want to use entropy or complexity in economics. Is it good or is it bad? So going back to the trend of entropy to always increase globally, if the nature of the universe is to maximize entropy, who are we to presume that that's bad? So I think the default assumption there would be for us to assume that that is a natural progression, that natural progression is a good progression. So with that said, let's look at income distribution. So for a log normal distribution, which represents income, Gini becomes 0.531 when the shape function, or when the shape factor is 1. And you can see is the before tax income in many of the developed countries, or many of the OECD countries, is actually right at around that level. So, and that the after tax Gini is well below that level. And so what we can conclude from redistributive wealth or redistributive taxes is that it reduces the economic complexity. And if the complexity of the economy is a good thing and something that we should seek to maximize, then that is actually a pretty strong case against redistributive taxation. So I'm going to shift here to the multivariate log normal, and following the same methodology for the univariate, we can come up with an entropy that looks like such. And this is really familiar because it has the same form as a Cobb-Douglas production function for constant entropy, which is an implicit assumption within the Cobb-Douglas production function. And it is also the same form as an ideal gas equation of state. So for us to go from the individual to aggregate to the group is pretty straightforward. We make some assumptions. Well, not really assumptions. We set the initial entropy to that term there and not as 1 because we aggregate it, we develop the entropy based off the individual. And so the macro entropy is as follows, and then we get this equation of state. The C and R here, I used the same notation that we use in physics to convey the meaning. They are not going to be the same numbers. But this is the ideal gas equation of state.
Carl, just sorry to interrupt you. I mean, we're sort of at 18 minutes here, so if we're going to your question.
All right. So we have solving for utility, measure in terms of the nominal currency. Utility is more of a function of exchange in space. So how I began to think about currency is that it is like we're exchanging a piece of economic space between each other, that the utility is tied actually to the value of the utility. And if economics is about people doing stuff, we really should use the units of doing stuff, which in our world is energy. And in the world of Bitcoin, it's actually in terahashes per Bitcoin, but that can actually be fairly easily converted into gigajoules per Bitcoin. Or in terms of the US economy, this is derived from EIA data. We could use an energy price index as a deflator. If we apply that to different levels of utility, or to our utility function for the individual, this is in the univariate model here, what we see is that beginning in 1998, the US had entered a recession that bottomed out in around 2010. When you look at every other indicator that we have, we show increasing entropy. So going back here, we can take our standard form to get to the ideal gas law, which shows a relationship between money and economic temperature, or expected utility. And we end up with a polytropic process. So if we look in the isentropic case, like say you're expanding hot gas through a turbine, you want that to be an isentropic process. and when you're doing, in that case, is you are extracting work from it. So I don't see quantitative easing as being stimulative. I see it as being extractive. And again, this is a subjective observation, and it's not about what we can control, but just what we've observed. Thank you.
Thank you, Carl. Thank you. I think we're unfortunately at the end of the talk without having too much question time available. I guess we'll mess up the whole schedule if we go into questions for 2 minutes here right now.
Right, I'm gonna exit.
Okay, thank you.